Hello guys, my name is Balkrishna Shivastav and welcome to Code with BK. So in this video we see how to free the memory occupied by a linked list in C programming. So before we begin, it is a request to please subscribe to my channel, and if any of my previous videos has helped you or if this video helps you out, so please do subscribe to my channel. Okay, so we have to free the memory that has been dynamically allocated to the nodes of linked list in C programming. And in this series about linked list in C programming, singly linked list in C programming, we saw what are linked lists from the very basic, from the very start. This struct node basically makes up a node in a linked list, and nodes when connected together using this next pointer reference, this creates a linked list. Nodes linked together forms a linked list. Okay, and then we saw each of these functions in detail. We saw how to find the length, how to get the value at this index, how to find the index of this value, print the linked list in reverse, insert at end, insert at front, insert at an index, delete front, delete last, delete at, and finally we complete this function. Okay, so how do we free the memory that has been allocated to linked list, the nodes of the linked list? So suppose if you have a linked list for 11, 1327. Okay, next, and null, and this is our head. Okay, all these nodes are dynamically allocated in our implementation of the linked list, and that is why we need to free the memory. Okay, whatever memory is dynamically allocated in the program must be freed before the program terminates, otherwise we have memory leaks. Okay, it means the program is occupying memory chunks which we are not using and we cannot reference them anymore. I'll explain what I mean by we cannot reference the memory anymore in a moment. Okay, all right, so in the memory what you have is, say for this linked list implementation, you have 5 struct nodes dynamically allocated. Okay, and each of these has its own x and next. Struct node has x and next. Okay, x and next, x and next, and x and next, x and next. Okay, so we have node with the value 4, 11, 13, 127. Okay, the next reference in this node with the value 4 stores the reference of 11, that means it is a pointer to 11. This means that the next variable inside this node with the value 4 is storing the address where this node with the value 11 is stored. Okay, because this is dynamically allocated, it will have a memory address which is stored in this next of node with the value 4. Similarly, the next of node with the value 11 has the address of this node with the value 13. Similarly, 13's next stores the address where this node with the value 100 is stored. The next of 100 stores the address of where this node with the value 27 is stored, and the next of 27 is null, or you can say this simply stores null. Okay, so in memory all these 5 struct nodes are dynamically allocated and they are linked like this. I have a variable, okay, head of type node pointer, which is storing the address of this node with the value 4. It means it is a pointer to this node. So this head variable stores address, okay, since this is a pointer, of the node with value 4. Okay, all right, now we have to free all this memory. So you have to free this node, this node, this node, this node, and this node. Okay, how do we do that? We say I take a node pointer current pointing to head. I say while current is not equal to null, okay, I say node temp is current is current dot next, and free temp. Okay, and finally set head to null. Okay, this last line is basically setting a pointer to null to indicate that it is not being used. Okay, once you free the linked list, there is nothing in the linked list goes empty, so you should be setting head to null. Otherwise head will still be pointing to the address where it was initially pointing to. Okay, so what do I mean by this is I take another variable current of type node pointer storing the address of what is stored by head, which is the pointer to this node with the value 4. Okay, this also stores the address of the node with the value 4, this variable current. of type node pointer. Okay, I say current not equal to null. This is storing some value, not null, true. So current not equal to null is true. Okay, you say temp is current, you take another variable temp of type node pointer storing the value in current. So say maybe this is addr say q. This also stores addrq. This also stores addrq. This also points to this node with the value 4. Okay, you say current equal to current dot next. So whatever address is in current's next goes to current. Current's next stores the address of this node with the value 11. So this also is a pointer to this node now with the value 11, and you can say okay addr of node with the value 11. Okay, it is a pointer to this node now. Okay, so this line is done, this line is done, temp is done, current equal to current dot next. Then you see free temp. When you say free temp, the memory at this location is freed. This temp variable is storing the address of this node. This is freed, this is given back to the heap. Okay, because all dynamically allocated memory comes from the heap. Given back to the heap, current is pointing to this node with the value 11. So this link is also lost. Okay, head is still storing the address of this original first node with the value 4. Okay, that's why we at the end have to set the head to null. Okay, free temp is done, loop finishes, you go back to the starting of the loop. So you lose the local variables in the loop, so you lose temp. Okay, all right, so this link is also lost, and your current is pointing to this node. Okay, this is after one iteration, this state of the memory after the one iteration. And similarly, we have to free all the other nodes. So we keep traversing current till to the next node till it is not equal to null, and we free the current node by saving it in a temp third variable. Okay, why do we save it in a temp? I'll tell you by the end of the video. For now, let's just complete this dry run. So current not equal to null is still true. Current is pointing to this node with the value 11. We take a variable temp, okay, of type node pointer again. Okay, fresh iteration of the loop. This variable is assigned again, equal to current, which is storing the address of this node, so pointer to this node. Okay, then you say current equal to current dot next. Current dot next is pointing to this, so current also points to this node with the value 13. Okay, temp is pointing to node with the value 11. Current is now pointing to the node with the value 13 after first two lines of the while loop. Then you say free temp. Temp is pointing to this node. Free the memory allocated at this address, so free this. Okay, and when the body of the loop is over, we lose local variable, so we lose temp and we lose this link. Okay, all right, so we have current pointing to this node with the value 13. Okay, node with the value 13. All right, after two iterations. So in two iterations, we lost two dynamically allocated nodes. So the number of iterations will basically free the entire list. Okay, then you check current not equal to null. Current is pointing this, not equal to null is true. You say temp is current. Again, fresh variable temp of type node pointer, storing the address where current is, storing the value in current, which is the address stored in current, which is address of node with the value 13, basically pointing to this node. So current also points to this node. Temp also points to this node with the value 13 after the first line. After the second line, current is storing current dot next. Current dot next is storing the node, the address of the node with the value 100. So now it stores address of node with the value 100. Okay, so now this link, okay, points to this node, and we have temp still pointing to this node with the value 13. Okay, and the next of 13 points to 100. So current is pointing to this node with the value 100. Next of 13 is pointing to this node with the value 100. Temp is pointing to node with the value 13. You free temp, we lose this. Loop is over, we lose local variable, we lose the variables in the scope of the loop. So this is lost. Okay, current is pointing to this node with the value 100. The next of 13 was pointing to this node with the value 100. This is also lost. Okay, because this memory is deallocated. There is no more variable next inside this node value 13 that is storing the address of 100. Okay, so after 3 iterations we lose 3 nodes. Again, current not equal to null is true. After this line we go back to check for the while loop condition. Node temp, again variable temp, you can take the variable here, temp of type node pointer, storing the address of the node with the value 100 because it is copying the address from current. Then you say current equal to current dot next. Now current points to this node. Okay, because next of 100 is pointing to this node. All right, next of node with the value 100 is pointing to this node. Then you say free temp. So temp is pointing to this node. This is freed. This link is also lost. All right, body of the loop is over. So we lose local variables. We lose this. We lose this node. Okay, so what is left is we have current left. Okay, temp is lost. Okay, this is corrected, this is given back to the heap, and we have current pointing to the last node with the value 27. Okay, all right, so now current is pointing to this node with the value 27. Okay, points to this node. Okay, you go back to check for while loop condition. Current not equal to null is still true. You said temp is current. You create a new variable temp of same type node pointer, copying the address from current. Current is showing the address of the node with the value 27, pointed to this node. So this also points to this node, contains address of node 27. Okay, you say current equal to current dot next. Current dot next is now null, so current becomes null. So current, this is no more a pointer to this node, and current now stores null. Okay, you say free temp. Temp is storing the address of this node. This is freed. While loop ends, this local variable is lost, so we lose this variable. Okay, all right, and we have by the end of this for loop, current equal to null, all memory for all these nodes given back, and when you say current not equal to null, it is false. Loop breaks, you come out. Okay, and then you set head to null because head is still storing the address of the where the very first node was dynamically allocated. So when you do this line head equal to null, it is then head is set to null. Okay, and this is important because you want head to be null. Okay, in order to demonstrate and represent an empty linked list. Okay, so after the function ends, we have head null and current null. Current will obviously be lost because it's a local variable. So after the function ends, this local variable is lost. Okay, so what you are left with after the function end is your head only pointing to null. Okay, and all this memory is deallocated. So in your memory, this is all given back to the heap. So you are only left with head equal to null. Okay, and all memory is correctly deallocated. If you mess up the order here, for example, if you say node temp is current, and then you say free temp, okay, and you say current equal to current dot next. Now this is a problem. Okay, this is a problem because in my memory, if I have again 5 nodes. Okay, so this again drawing the same memory diagram for this very list. Okay, drawing a fresh memory diagram. 5 nodes dynamically allocated. Next of 4 is 11, next 11, next of 11 13, 13 next is 100, and next is 27. Okay, when you say temp equal to current and current is pointing to head, so you say we have a current, okay, equal to head, and we also have temp pointing to head. Okay, so you have freeing temp first, you are not moving current equal to current dot next first. When you free temp, this is lost. Okay, and then you say current equal to current dot next. When you free temp, the memory here is deallocated, so we do not have the next location of current anymore stored. So current dot next is supposed to be this, but we cannot get to this anymore because whatever data memory was there has been deallocated. Okay, so when you do current equal to current dot next, now it is an undefined behavior. Okay, so access to the remaining linked list is lost. That's why we save temp to current first, we move current equal to current dot next first so that we can move on to the second node, and then we free temp. Okay, that's why this order is correct and this order is wrong. All right, okay, and this is how you free your linked list in C programming. Okay, so let me just quickly add this code and head equal to null. Okay, so whenever you call free, you can set head equal to null. Okay, so after my code, I'm gonna say free head. Okay, so whatever memory is dynamically allocated is freed. Okay, so gcc ll free.c conflicting types for free. Oh, free is already used, right? So I can use free linked list, and I can use free linked list and free linked list. Okay, right? This should be better now, because we are already, there's an inbuilt free method, right, that takes a void pointer. So there is a clash. This is okay now. Okay, and you see this free method is actually deallocating all the memory. Okay, so one last thing to note here is, and then it is a common mistake that you are setting head to null here, but you're not setting head to null in this function. So after this function returns, this head still points to the original address it was pointing to. So if I say printf head is at %p \n and I print the value of head. Okay, so before freeing and after freeing, the head will be pointing to the same address. You see, same address. Okay, because when you set head equal to null in this function, the local variable that was given to this function head, a copy of the original head, is being set to null. So the changes made to this head will not be reflected back, and that's why we return the updated head pointer every time we insert or delete. Okay, so it is recommended that after you free head, you set head equal to null separately. Okay, all right, now head is at 0 0. Okay, this statement is redundant here, but you should keep this to remind yourself that you should be setting the head to null after you free the linked list. Okay, all right, so this was your code and concept that goes behind freeing a dynamically allocated linked list in C programming. All right, if you don't have nodes dynamically allocated, do not free them. For example, if you look at this this linked list that I create by using the node variables, okay, and these nodes are not dynamically allocated. Okay, these are 5 variables. This memory goes on the stack memory, dynamically allocated memory goes on to the heap memory. So I connect them, I give them values, connect them, and if I print them, let me just simply print them, I get 1 2 3 4 5. Okay, all right, but these are not dynamically allocated. So if you try to free head, you will get a error. Okay, because this is not dynamically allocated. You don't need to free the memory that was not dynamically allocated. All right, but we don't use this approach, because if we want to have 200 nodes, we cannot have node n1 n2 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 till 200 and we keep connecting. Okay, in order to have a linked list of 200 nodes, I'm going to create an array. Okay, with all the values that I need, I'm going to iterate the array, and I keep calling one of these insert at end or insert at front function. Okay, all right, so this was everything about freeing the memory occupied by the linked list in C programming, and we usually use dynamic memory allocation to allocate memory to linked list. Okay, and that's why we need to free the memory as well. Okay, one last. Okay, right, so I hope this video was helpful and you like this video. So if there is any doubt, there is a part you do not understand, please let me know in the comments. I always try to answer all your comments, and you can also let me know in the comments if there is a question you want to solve, or if there is a concept you want to discuss. So please like this video, subscribe to my channel, and thank you for watching.